Good morning, everyone. Welcome to Teledyne ISCO's October webinar, focusing on general chromatographic techniques for natural products purification. Today's webinar will be presented by Jack Silver, Teledyne ISCO's application specialist. If you have any questions or comments during the webinar, please use the chat function within the Zoom platform. And Jack will have time to answer all questions at the end. At this time, I will turn it over to Jack to get us going.
Hello, Jack here. We're going to talk about general chromatographic techniques for natural products purification. And the first thing we're going to talk about is an agenda. That would be the initial steps, things that you should do before touching your plant extract or your natural products. We're going to talk about wide polarity range chromatography and how it fits into column screening, the options that you can use for column screening, and we're going to talk about self-packed columns that you can run on automated flash systems. Although this webinar is geared towards automated flash chromatography systems, the techniques can be used if you are using glass columns. You might not be able to run a gradient as nicely as an automated flash system, but you may still run a step gradient, and you can still use the column screening to help your natural products. Natural products are different in that we don't know what we have until we purify it. We have an unknown product, and therefore we have unknown chromatography. And what that means is that we have to do some sort of screening. The initial steps prior to even extracting anything is to search the family, genus, and species. If you're working with a bacteria or fungi, try to identify what it is insofar as you can. Plants, even at the family level, many families produce similar compounds. Generate a list of known compounds and existing purification methods, and I find that saves a lot of time because we can screen out known compounds more quickly. Such sources of information are the Journal of Natural Products and an ACS journal search. And I've listed a couple of websites below, Chebi and PubChem, Science Direct. Also, you can do a search as well. Again, look at the species and the family and see what you find as well. Also, look at the literature for the assay that you propose to run. If you're running hypothetically a PLA2 assay, look that up in the scientific literature. Alkaloids are very common in central nervous system screens, and I find phenolics are common in antioxidants as an example. The fact that you find certain classes of compounds also suggests purification methods. For example, alkaloids are easily purified on ion exchange columns, and when they come off the ion exchange, they are often ready for prep HPLC without further workup. It does suggest purification strategies. Also, look at your internal databases. If you think that you have a similar compound, see what's been run already at your company. Columns that I like to use for screening include normal phase, silica, alumina, and diol, and reverse phase. Separate from those are ion exchange columns, and those are generally self-packed columns, strong anion exchange and strong cation exchange. These columns have all different selectivities, which means that they retain molecules differently from one another and allow you to purify compounds and see which column works the best. The other thing I will discuss is wide polarity range chromatography. Wide polarity range chromatography uses a range of miscible solvents to elute compounds off of a column. You start off with a weak solvent and use a succession of stronger solvents to elute compounds. The The reason why I would do this is it reduces greatly, almost eliminates the chance that I will leave an active compound on a column. It provides an approximation of the compound polarity. If I see where the active compound elutes, or where a family of active compounds elutes off of a column, that suggests a further purification strategy. Because I'm going to a very strong solvent at the end, it provides the best opportunity to elute unknown compounds, and it can suggest other solvents that might be useful. I mentioned strong and weak solvent, and the strong solvent is the solvent that causes the compound to elute down the column. If I'm running hexane and ethyl acetate would be the strong solvent in normal phase. If I'm running reverse phase, running methanol and water and acetyl nitro, the acetyl nitro would be the strong solvent. The other thing I'm going to talk about briefly is solvent selectivity and polarity. In this list, the polarity is in parenthesis, and depending on if you're running normal phase and reverse phase, for normal phase, the more polar solvent tends to be the stronger solvent. If for reverse phase, the more polar solvent tends to be the weaker solvent. I have a selectivity group over here, and solvents in the same group tend to have the same selectivity, that is the elution order for compounds. So for example, in group 1, I have a couple of ethers listed there. If I'm running isopropyl ether and I change to ethyl ether, I'm not going to see improved chromatography. I might see a different chromatography if I use, say, tetrahydrofuran instead of, say, diethyl ether, because they are in different groups. Again, the general method for wide polarity range chromatography is using a weak to a strong solvent. On our systems, on our automated flash systems, we can use automatic solvent switching. If you're using an open glass column, you just change the solvent. The one key is the solvents have to be miscible. So in the example below, running a diol column with green tea extract, I'm running hexane to isopropanol, and then I change the solvent system from isopropanol to an isopropanol water system. And you can see that when I changed the solvent system over, I got some more compounds that eluted off. We're going to use capsaicin as an example to simulate an active compound. This has been extracted from green chili peppers, and I used a variety of detection techniques. I used UV detection, all wavelength collection, which allows me to look at all of the wavelengths in my UV-Vis detector, light scattering detector, and mass-directed fractionation with a mass spectrometer. I loaded 750 milligrams of extract on each 12-gram column. This sounds like an awful lot of material. However, the active compound is usually present in very small quantities. So we can still manage to get very good chromatography. And except for the ion exchange, where the sample has to be dissolved in solution to be ionized, I use solid load cartridges so that I didn't have to worry about the solubility of the sample in the different solvents. So normal phase wide polarity range chromatography was run on silica gel. My gradient over here is hexane to ethyl acetate to methanol, and methanol to water. So I'm consistently going to a stronger solvent. Silica gel works very well with methanol and water as long as the silica gel is kept in neutral or acidic. In other words, don't use ammonium hydroxide or basic modifiers because they dissolve the silica. As long as the solutions are neutral or acidic, you can run these very polar solvents. The detection was 254 nanometers using the ELSD and the mass spectrometer. And the one thing to note is even though I have a very, very crude sample, the crude plant extract was loaded onto the column, I'm seeing some very clean mass spectra from some of the peaks over here. So you can use mass spectrometers to screen compounds even at this early stage. And if you can correlate the activity with a known mass, your work becomes a lot easier because you have a potentially known compound that you can purify much more quickly. Another example is using the diol column. And in this case, I use hexane to 2-propanol to water. You can use the same solvents that I did for silica, and I would actually recommend doing so. I simply wanted to show a different sort of wide polarity range chromatography. In this example, capsaicin either failed to elute or it was a very broad and weak peak because I could not see the capsaicin peak in any of my the peaks that I detected with the mass spectrometer or with the UV. Why would I want to use diol over silica? Well, diol is a weaker column. It doesn't retain compounds as strongly as silica gel. It also has a different selectivity than silica, and sometimes compounds that don't run well on silica run well on diol. Diol is also very useful if I'm running delicate compounds that might decompose on silica gel. Another run was with alumina. Again, hexane to ethyl acetate to methanol to water. And alumina is different than the other two normal phase media. And we can see that the major peak that we see with the mass spectrometer is indeed the capsaicin. We can see that through the mass spectrum. I can see a peak at 306, which is the M+H. I can also see a 328 peak, which is the sodium adduct. The capsaicins actually eluted pretty cleanly off of the diol column, although they are all together. They eluted as a family. So there was selectivity between the capsaicins and other compounds, but there was no selectivity between the various capsaicins themselves. For reverse phase, I ran Redisep Gold C18. The gradient here was water to methanol to dichloromethane. Going from methanol to dichloromethane is called non-aqueous reverse phase, and we have some application notes on that. That is very useful for very, very non-polar compounds. What we can see is that the capsaicin compounds were resolved from one another, and we can see that in the mass spectrometer. However, we could also see that there are a number of other impurities that were not resolved from the capsaicin. So what we learned is that the cleanest purification of the capsaicin class was from the alumina. C18 can resolve the individual capsaicin compounds, and we detect the capsaicin as the M+ sodium on the mass spectrometer. So that provides a little warning to us when comparing eluted peaks. Remember to look at adducts, remember to look at fragments. For example, if the active compound potentially is a steroid compound, it might not be visible in electrospray, but you might see it in APCI, and steroids often show up as the fragment with the loss of water. Column screening allows correlation of activity and compound mass, and it also gives us a sense of where the compound elutes. So putting it all together, the capsaicin peak from the alumina was run on C18. So I took the peak that was on the alumina and then took that and ran it on C18. So I'm going normal phase to reverse phase. So that's an orthogonal purification technique where I'm using a very different type of column chemistry. The C18 gradient was flattened to improve the resolution. So on the screening run, I ran from about 5 to 100% methanol. I don't need to run the beginning part of that gradient because all I have are the capsaicins. So I can flatten out that gradient and elute the peaks a little faster. Also, because the compound eluted in methanol water, there was no need to run the non-aqueous reverse phase portion of the gradient. I didn't need to run the dichloromethane portion. And so what I got was the run depicted here, where I have 3 major compounds purified and identified: capsaicin, dihydrocapsaicin, and homodihydrocapsaicin. This purification screening, the C18 column screening suggested this purification, and because those compounds eluted fairly late, it suggested that I can run the gradient that I have here. One question you might have is, well, I purified the compound from peppers. Why is capsaicin not the largest compound? One reason for that is different peppers produce different compounds in different proportions. You might find that different strains of plants, different species of plants produce compounds in varying proportions. In fact, the alumina run was so clean that you could run it on a prep LC system and get very good peaks. Please understand that this is not the sample that we had in the previous slide, but it does contain the first 2 eluting compounds. In other words, the capsaicin and the dihydrocapsaicin. However, I have excellent resolution between those, and I will tell you in a future webinar how to produce a gradient like that from your analytical HPLC. So stay tuned. We're going to talk about some specialty columns, and then we will come back to column screening. Capsaicins they only have a single or a hydroxyl group, and so they don't work very well on ion exchange. Self-pack columns tend to be specialty columns. They might be difficult to pre-pack. Some examples that are commonly used for natural products are CHP-20, a polymeric reverse phase. It tends to swell a little bit in solvents. Sephadex LH-20 is very widely used for cleanup. It's a normal phase column. It also works by a size exclusion mechanism. Polyamide is a reverse phase column, and it's very good for phenolic compounds. Ion exchange columns are very good for alkaloids and other bases, phenolics, and other acid columns. Why would you run a self-pack column, essentially a glass column, on a flash system? Well, we have pumps that have solvent management. We can control the flow very accurately, so reproducibility when you run the column the next time becomes a lot easier. We have a detector and a fraction collector built into the system, so you have almost everything you need to run essentially an open glass column with the system. And as an example over here, we have a Sephadex column that's hooked up to a CombiFlash NextGen system. The compound eluted as a band, and I used it to clean up a phenolic compound. After the phenolic compound was cleaned up, I used a Redisep C18 gold column to purify epigallocatechin gallate and epigadican gallate. Polyamides are a reverse phase technique, and it's very useful to remove tannins. The other thing is that aside from removing tannins, we have a series of peaks. In the chromatogram below, I see 1, 2, 3, 4 peaks. One of them is a shoulder. And again, I used wide polarity range chromatography using the gradients listed on the right side of the chromatogram. And so I took those peaks and I ran them on a prep HPLC. And what I got was 4 runs, and even though I'm running a gradient, those are still very complex mixtures. So the polyamide was a useful technique to simplify the mixture and then purify the compounds. Self-packed ion exchange. This is a strong anion exchange, and you can use that to purify acidic compounds. This compound was a quaternary ammonium resin. I had to replace the chloride counter ion with acetate before use because that's a weaker ion than the chloride than the column came with. If I didn't wash off that chloride, I would have very little capture of the compounds. The compounds that were captured from the ion exchange were greatly enriched because I removed the neutral and basic compounds, and in fact, it is almost ready for Prep LC. And I used about ½ a gram of crude extract on a 15-gram strong anion exchange column with liquid loading. The other type of column is a strong cation exchange column. This was a sulfonic acid-based strong cation exchanger. It was conditioned with 1 normal sulfuric acid to form a proton counter ion, which again is very easy to displace with the alkaloids that I want to purify. Again, I used ½ a gram extract for 15-gram strong cation exchanger. It was liquid loaded, and I dissolved the sample in methanol containing acetic acid. The acetic acid caused my alkaloids to become ionic. It's very useful for enrichment, and I removed the neutral and acidic compounds. So my conclusion is, before purification, do a literature search. Column screening allows determination of best initial purification conditions. After the column screen, I can then optimize the chromatography. Column screening can be used to suggest follow-up purification strategies. So as we could see with the capsaicin example, I found that I can purify the class nicely with alumina and then use C18 to clean it up very easily. Wide polarity range chromatography allows for complete elution of unknown compounds, and it complements the column screening because it suggests the polarity of the active compound.